Okay, number one on the review, a manager wants to determine the proportion of employees that arrive late to work. She will call a company meeting to see if there is clear evidence that this proportion is greater than 10%. She selects a random sample of 30 employees. So the data is from a random sample. It checks that. At this company to test a hypothesis, the null is nothing's unusual, 10%. Alternate is we think more than 10%. Which condition for inference has not been met? So is that less than 10% of the population size? So the sample was 30 employees out of 500. So 30 is less than 10% of 500 employees. So that condition is checked. Let's do NP and NQ here. So that would be 30 times 0.1. which is 3, is that greater than equal to 10? That's not actually true. So I think this is the one that is not been met, that the condition for inference has not been met. So I think it's C. Which of the following will increase the power of a test? Okay, so you might want to think about that chart. I don't know if this helps you, but I think about this, to me, helps me. When you, this is type 1, which is the alpha level. This is type 2, which is the beta level. This is the power of the test, which is the correct decision. This is when you reject. This is when you fail to reject. And this is when the null is true. And this is when the alternate is true. Okay, so to me, okay, so power goes up. Let's see. Type 2, increased type 2 actually makes power go down. So that's not true. They have those two add up to 1. So those two values, if power is 20%, type 2 is 80%. They always add up to 1. Increase the sample size. But yeah, that should work, actually. But let's just see the rest. Reject the null hypothesis only if the p-value is smaller than the level. So that would be the correct decision. So correct decision, we reject. But that's not really increasing the power. That's just saying it's a correct decision. So I don't think that's it, although that's at least tempting. Decrease this alpha. So when alpha goes down, the power actually goes down. They kind of word in conjunction because alpha goes down, beta goes up, power goes down. So I don't think that's it. So I think it's B. In a large Midwestern university, a simple random sample of 100 freshmen in 2014 found that 20 finished in the bottom third of their high school class. In 2016, another simple random sample of 100 freshmen found that 10 finished in the bottom third of their high school class. In both years, the entering freshman class had roughly 6,000 students, so pretty big school. Let P1 be the proportion of all entering, okay, so forth. Is there evidence that the proportion of freshmen who graduated the bottom third of the class in 2016 has been reduced compared to the proportion in 2014? So P1, let me just say about this. So P1 is be the portion in 2014. So P1 is that one. And so P2 is 2016. It just takes me a second to do this. So has it been reduced compared to 2014? So is P2 smaller, basically? So P2 would be 2016. If that one's smaller there, so P2 is smaller, then we would get a positive answer. So we are going to choose greater than. So that is I just want to make sure how that works. You kind of have to think through the null. We want a greater than. We want P1 to be larger than P2. We think it may be reduced. But the null is there's no difference, right? Same proportion both times. Okay, the test statistics. So that when it says that, that's the z value there. So z is, so if you kind of draw a normal curve, 0, -1, 1, 2. So 1.98, kind of shading out here, starting at a z value of 1.98 and getting bigger. So what's the appropriate p-value and conclusion? So you would want to get out your calculator. Let's do, Okay, so menu 652 is norm CDF. We want a lower bound of 1.98. These are Z values, and then an upper bound of infinity or a really big number. You can leave the default because it's a Z value there. And so we get 0.023. So a P value of 0.023. Okay, so that should eliminate some answers. Okay, so, or it might round up. Okay, so it's got to be one of these because those are, oh, one of these, yeah. So the alpha level is 5%, so that's 2.3%. So it's pretty low. So we should reject here. So I don't think it's going to be failed to reject, failed to reject. It's got to be reject. It's got to be D. Because we rejected because our p-value is so low. We had evidence because we have such a low p-value. In a test of statistical hypothesis, the p-value tells us if the null is true, if the alternate is true. So the generic thing I'm looking for is, given that the null is true, what's the probability or the chance that the alternate is? So it needs to be say like, I'm looking for wording like this. When the null is true, the probability of getting evidence for the alternate as strong or stronger than the observed evidence. That is actually a really nice definition of that. Okay. A marriage counselor claims that the divorce rate in the United States is 30%. She would like to determine the divorce rate is greater among couples from the United States that have children within the first 2 years of marriage. That could be tough, I guess. The true proportion of all couples having children within the first 2 years of marriage that get divorced. Which one of the following sets of hypotheses is appropriate? Okay, so just a hypothesis. The null is nothing unusual is going on here. So I don't think C makes sense for the null, right? We think 30% is the average, right? Ooh, I didn't notice that. Do you see these two? They can't be it because do you see what they used? P hat to describe. My eyes are kind of bad, but I barely saw that P hat there. It can't be P hats. You can't be talking about P hats when you're talking about the population parameter there, which is P, the true proportion. So it's either less than or greater than. So the proportion is greater among couples. So we are looking for this guy. So it's got to be E for 5 because of the word greater there. Yeah, okay. Simple random sample of 45 male employees. A large company found that 36 felt the company was supportive of female employees. Independent simple random sample of 40 employees found that 24 said they were supportive of female employees. Okay, so you have the proportions there. P1 is the male and P2 is the female. Okay, so what we want to test the hypothesis that the null is nothing unusual. Guys and girls have the same opinion there, proportion. The alternate is that the males is greater than the females. Maybe the males think, oh, the females are great. We don't have any problems. Which of the following is the correct test statistic? Okay, so we want to do the, so the males, P1 is the males. And so P hat would be, in this case, 36 out of 45. And this is the, I'm gonna put males there, but that's P1 basically. And then P hat 2, which is kind of like the females, I'm gonna put F there, but that's the second one, is gonna be 24 out of 40. So let's get our calculator out. Okay, so 36 divided by 45 and 24 divided by 10. 24 divided by 40, maybe. Sorry about that. Didn't make it in logical sense. 0.8 and 0.6. Okay, so we do want P1 minus P2. So 0.8 minus 0.6. But that's all of them except for this crazy one. That's definitely not the form of the answer there. Okay, and even like D, you can see that's not a formula we've learned for standard deviation for proportions. So it's got to be one of those guys. Okay, so what we should have here, so this looks like a 2-prop test. So to get the values, we do use p hat pooled here. So the common value would be the 36 plus 24 over 45 plus 40. So let's get our calculator out and find out what p hat pooled is. 36 plus 24 over 45 plus 40. 12/17, which is 0.705. Okay, so 706. So it's not this one, right? That's using, you can kind of tell that's using the p hats there. And so we need to use the pooled proportion for this one. So what's the difference? They look pretty similar for these two. Let's see. So the correct answer is B. I'm trying to look at this. Is there any difference in the answers? I just don't see much of a difference. Do y'all see a difference there? Z equals, maybe I'm missing something obvious, but those like B and C look completely alike to me. I just don't see the difference there. B is right. Maybe C is right also. If it's the same, maybe y'all have better eyes than I do, and you can see. I'm probably missing something obvious there, but they're both plus signs, minus signs. It looks like the same answer to me, so I think that's probably a misprint. Suppose you are conducting a test of significance, which the null is 45%. Which of the following test of a specific alternate hypothesis has the greatest power? Okay, so let's think about some of the things that make us have more power. So we take a larger sample size, that's going to give us more power. So that goes away. 50 is the larger sample size. Alpha goes up, power goes up. They go up hand in hand because alpha goes up, beta goes down, which means power goes up. So I want a larger alpha value, so I'm getting rid of the lower alpha value. So it's either B or C at this point, I think. Okay, and so I want a bigger difference from here. I want my result of my sample to be, I want it to be a larger difference of 0.45. So which one's further away? 0.48 or 0.51? I think 0.51. That gives us more powerful results when the p-value is more different. I like that question, actually. Your friend found a die sitting on the shelf in the stats class. He started to roll it, suspects that it might be a trick die. In 120 rolls, the number 1 has come up only 10 times. You suspect the die is producing fewer ones than it should. Let p equal the true long-run proportion of ones, which is following is appropriate p-value for this test. Okay. Even if you want to use your calculator for this, you want to do the null and the alternate to start with, just because you kind of have to ask that question. So the null would be p equals the null is a die is fair, so p equals 1/6, right? I think that would be the null. So the alternate, I guess there's a colon there. But p is, let's see, what's 10? We think it's less than 1/6, where p is the true proportion of ones that are rolled. So we don't, the null is, this is not a trick die. This is a normal die. It's 1 out of 6 chance because there's 1 out of 6 faces have a 1 in them. And then we think the alternate, we think it's coming up less than that. So maybe our p hat, so you can get out your calculator and check out your p hat there if you need to. Like our p hat, just right as it is 10 divided by 120, which is 0.08. So that's like 1 divided by 6 is 0.16. So it is, you know, definitely below that, but is it enough to prove the test? So at this point, I might consider doing this one in my calculator to get the p-value. although you probably should check the conditions. Is it a random sample? Is it less than 10%? And is it NP and NQ? So if we, in 120 rolls, 1/6 of that is more than 10, less than, okay. You can check those conditions. It seems to pass. So I'm going to go do this in my calculator, 675, I believe. And so you get the one prop z-test there. So this is going to be, the null is 1/6, which was, I have to go back to that, 0.08, 0.1666. Okay, so menu 675, 0.166666. Successes was 10 out of 120, and the alternate is less than. So that's why I had to do the alternate. And so it should give me a p-value of, the z-value is negative 2.44. That's tempting there, but they asked for the p-value, I think, which was 0.007, 007, like James Bond. So there it is. Should be a B, and it is. Sociologists hypothesize that couples who have a child within 3 years of marriage are more likely to divorce than those who do not have a child within the first 3 years of marriage. From city records, she selects 2 independent random samples, one of a couple of a child within the first 3 years of marriage, and one couple of couples who did not have a child within the first 3 years of marriage. She compared the divorce rate of these 2 samples. The p-value for this one-sided test is 0.0314. Using alpha is 0.05. So really, if you just know those 2 things, you could probably make a decision here. So what's that going to be? So our p-value is 3%. Our alpha level is 5%. Do we have convincing evidence or not? So I'm tempted to say this is the answer. Divorce rate among couples that have a child within the first 3 year marriage. The divorce rate is greater among, so man, I think that's probably it. It's definitely not this one. We are going to reject. If you decrease your chance of getting divorced, it is better to marry later in life. So these are implying causation, which I don't think this is an experiment, right? It's random samples. There's no random assignment. So I don't think we can kind of imply causation here. So I don't think those are true. So it's got to be A. If a significant test has a p-value 0.005, the null hypothesis is true. Do we ever say the null hypothesis is true? We never accept the null. That's not the case. We have proven the null is true. No, that's not the case. We do not have 0.005. So that is below an alpha level of 5%. So we would reject the null. We do have convincing evidence. So it's got to be D. Yeah. Because 0.5% is below any reasonable alpha level. Okay, pre-response. So expect on the test, you're going to have 1 prop z-test and 1 2 prop z-test on this one. So show how you work. Okay, so Mark, a starting player for a major college basketball team, made only 40% of his free throws. Okay. During the season, during the summer, he worked on developing a softer shot in hopes of improving his free throws. In the first 8 games, Mark made 25 of 40 free throws. You want to investigate whether his free throw percentage for this season is more than 40%. Is there convincing evidence that the 1% significance level of Mark's free throw ability has improved? Wow, 1% is pretty strong. Okay, so what's the null going to be in this case? So the null is that P is equal to 40%. Nothing unusual going on. That's an O there. Alternate would be that we think he's gotten better. He's been working on it, so it's greater than 0.4. Significance level, the alpha level is 0.01. Alpha is 0.01. And define the parameters. So you would say in words, P is the true proportion of free throws that Mark makes this season. Okay, So something like that. Okay, so then plan, you want to name the test. So this is a one prop z-test. You're going to check the conditions. So the first one is random sample. So it's not clear. It's a random sample. I mean, 25 or 40 attempts. We're going to call that random sample. So it's going to pass the random sample condition. Less than 10%. So 40 is less than 10% of all free throws throughout the season. The NP and Q, so this is going to be 40 times, we know P is 0.4, so 0.4. We hope that is greater than or equal to 10. And then 40 times 1 minus 0.4, or 0.6, we hope that is greater than or equal to 10. So for 16, I think this is maybe 24. So those are both greater than or equal to 10, so it passes the conditions, passes all the conditions. Okay, the do, P hat, is going to be 25 out of 40. Let's see if we can think about that. It's 5 out of 8. So 5 divided by 8, that's at 6.65. Okay, Z is going to be a fraction. It's at the P hat, 0.625 minus 0.4. So that is a, pretty big difference. I'm thinking this might work here. We'll see. Maybe he really did improve. Square root of, and because this is a test, we know the p-value. We're going to use the p-value here. So it's going to be 0.4 times 0.6 up top over 40. You're going to type that in your calculator. So 0.625 minus 0.4, whoops, divided by a square root of 0.4 times 0.6 all over 40, 2.9. Wow, so this is going to work here. So that's the z value. You got to draw your curve. Say that's 0, 1, 2, 3. There's like a tiny area out there, very tiny. You're going to do your norm CDF in your calculator. So menu 652, 2.9 to infinity. Default for Z, 0.001. So 0.001 is our p-value. Okay, because we have, so you start you say, okay, because our p-value 0.001 is less than our alpha level of 0.01, we reject the null. We do have evidence to say that Mark's free throw percentage has improved this season. Interpret the p-value. So given that the null is true, so given that he shoots 40%, there is a 0.001 chance that the alternate is true here. Let me see what they said. It's hard to do that one. So 13, these are the results they said. Because we failed to reject the null, it is possible that we have, this is for 13. This is 11, sorry. 11 is this one, okay. So part B, assuming Mark's free throw ability for this season is the same as it was for last season, that is, he will continue to make only 40%. There's a 0.001 probability of getting a sample proportion of 0.625 or greater just by chance in a random sample of 40 free throws. Said very well there. By the way, one thing they did do is they did the test in the calculator as well, which is a good idea. So I never double checked myself with the calculator. So you can do that pretty quickly. You can go menu 675. This was 0.4. We did 25 out of 40, and our direction was greater than. And so that should double check those values to make sure they kind of match here. And always a good idea to do that. You'll catch some errors sometimes that you make, all of us do, and great thing to do to check your answers. Do political attack ads work? Well, we see them sometimes this time of year when there's an election. A congressional candidate who currently has the support of only 44% of voters who runs a television spot that aggressively attacks the character of his opponent. He wants to know if the television spot has changed his support level among voters. Define the parameters and state the null and alternate hypothesis for this test. Okay. So define the parameters, state the null and hypothesis. Okay, so the null would be that the proportion is 0.44. Nothing unusual. That's what we say, and that's what it is. The alternate would be that the proportion is not equal to, it looks like the way they phrase this, what has changed. He wants to know what the television spots has changed, his level of support. We think it's still 44%, nothing unusual going on. P is the true proportion of folks that will it currently has a support of only 4 that will support his candidate after watching an attack ad. Suppose his pollsters plan to survey a random sample of 450 voters and conduct a two-sided test of the null is 44, the alpha is 0.05. They determine the power of this test is 0.4. When P is 0.4 is 0.36. Explain what that means in the context of the problem. So can you interpret the power of the test? Okay, so power equals 0.36. Okay, so the power, you want to start with something like, given that the null is true. So given that the true proportion of free throws made is 44%, there is a 36% chance that the alternate is true. In other words, that he is actually shooting greater or not equal to 44%. So this is how they said it for part B. So 12B, I just want you to see their wordings. It's hard to get that exactly right. So if the true proportion of voters that support the candidate running the television spot is P equals 0.4, there's a 36% chance that they will find convincing evidence for the alternate that P is not equal to 44%. That's pretty close to what I did. Okay. So 12C. Describe 2 ways pollsters can increase the power of the test. So the sample size could increase. So if you increase sample size, that is going to increase the power. And then alpha, which is the type 1 probability of type 1 error. So if the alpha level increases, that also increases the power of the test. So those go in conjunction. Alpha goes down, power goes down. This would be the easiest to affect. We don't have a control over how different the values are usually. Pollsters survey a random sample of 450 voters to find that 186 support the candidate. This produces a 95% confidence interval for the proportion, and that's the proportion. Use the confidence interval to determine whether this test would reject or fail to reject the null. So let's look at this. So support is this. They find that 186. So I think we need to get our calculator out and say, okay, 186 divided by 450. Do we need this or not? Let's see. That's 41. Actually, I think let's look back to the null. So the null is this, right? So that's really what we're testing here. So is the null in our interval? So it's 44%. So is that between 36% and that? And it is. So because the null is inside of our interval, it's one of the plausible values. We don't have evidence to say that we would fail to reject. We don't have evidence to say that the null is not a plausible value here. It is, and so we're not going to reject the null because inside of our interval, it's one of the plausible values. Okay, finally, one more thing. We've got a 2-prop z-test to do. It seems to be becoming more common for students to live in off-campus housing than to pay to live on campus. A study at a large state university revealed that in a random sample of 50 seniors last year, 56% lived on campus, off campus, whereas a random sample of 50 seniors showed 64% lived off campus. Is there convincing evidence the true proportion of all seniors living off campus is less than this year? Okay, so what's the null going to be? We're going to start with the null. I'm going to say probability of L, P sub L, that's probability of last year. This is a colon there. Minus probability of this year, and use a T there, is equal to 0. There's nothing unusual. The proportions are the same. The proportion of last year's seniors living on campus, same with this year's. The alternate would be that the proportion of last year's minus proportion of this year's. So we want last year's to be less, is less than this year. So that means to be a smaller number minus a bigger number, which is going to be negative. So I think we want it to be that way. Or P of L is less than P of T. Okay, so the alpha level, you just want to state it, is 0.05 if they don't say anything. You want to define the proportions. I'm not going to write it all, but proportion, the true proportion of last year's seniors who lived off campus is P of L, and then P of T is the true proportion of this year's seniors that live off campus. Okay, we're done with the state. So then our next step would be to plan. So check, name the test. So this is a 2-prop z-test. Check the conditions. So does it say something about a random sample? Yes, so random sample. Okay, less than 10%, so 50 in both cases is less than 10% in both, for both this year and last year. And then NP, so this would be 50 times 0.56. Must be greater than or equal to 10. You type that in your calculator. 50 times 1 minus that, or 0.44. That has to be greater than or equal to 10. And then 50 times 0.64. The second case, that has to be greater than or equal to 10. And 50 times 0.36, or 1 minus 0.64. That one has to be greater than or equal to 10. So you type those in your calculator, make sure those are all good. We're ready to go. Okay, then you're going to do p hat. In this case, you probably want to do all three. I think you're going to, well, no, p hat common. So you want to get the number here. So I'm going to use the calculator to calculate that. So it just seems to make sense. So I think the first one is 56. So 50 times 0.56 and 50 times, I think it was 0.64. So 28 and 32. So the two individual number successes is 28 and 32 over 50 plus 50. So in your calculator, that would be 28 plus 32 over 50 plus 50. That's funny. 50 plus 50, 0.6. So our p-hat pooled, our common value is 0.6. Okay, so we're going to use that in the calculations here. So then z's a monster here. So the numerator is going to be p-hat L, which is, or P of L, which is going to be 0.56 minus 0.64. You can say minus 0 there if you want for that last part, but you can just leave it like that also. Square root of, we're going to use our p-hat pooled value here for both of these fractions inside of here. So this is going to be 0.6 times 0.4 for both of them. And I think they both had sample sizes of 50. So you type that whole giant thing into your calculator, you get your Z value there. So you do 0.56 minus 0.64 over square root. 0.6 times 0.4 over 50 plus 0.6 times 0.4 over 50. And hopefully that's right. Okay. If it is, we can do norm CDF, so menu 652. What was that value? Negative. So we draw that. So maybe I should write negative 0.816. So 0, negative 1. So like right around here, we're shading this way, starting at that Z value. So this would be menu 652 there to negative 0.816. And that's p-value 0.207. Let's just double check all of this. So menu 676 is 28 out of 50 and 32 out of 50, and I think it was less than. So p-value 0.207. Oh, everything's good. Okay, and it even gives you, I really like it, gives you p-hat pooled there. You can see it's 0.6. It's just called p-hat, but that's p-hat common or p-hat pooled there. So it's really nice to remind you that there is a value of p-hat pooled, especially for the 2-prop Z test. So it's what we use for the 2-prop Z test. Okay, so now we have to make our conclusion because our p-value equals 0.207, which is less than our alpha level of, I'm guessing 0.05, and it is, wait, 0.207 is not less than, is greater than our alpha level. So 20% is greater than 5%. We do not reject, or we fail to reject. We do not have evidence that the true proportion of last year's seniors compared to this year's seniors, of seniors living off campus, is any different from each other. We don't have evidence to say that's true. Which mistake did we do? So we failed to reject, right? So we did not reject. So we failed to reject, which could only possibly be a type 2 error. So if we made a type 2 error, that means we failed to reject when the null wasn't true. The alternate really was true. So we thought there's no difference, but there actually was a difference, right? The alternate was true. And so in this case, we didn't think there was any difference. So we didn't think there was any need to build any more buildings, but maybe we should have built another dorm to accommodate these folks because it seems to be growing, that the attendance does. Something like that. This is what they said for that one. We did not find convincing evidence, the true portion of that, when in fact true portion is less than that this year. Oh, they didn't ask for a consequence. I was thinking about a consequence there. And again, it just shows you the steps there. That's a really long screencast, but hopefully you didn't watch every problem, maybe just the ones you needed. That's it.